Hello my friends, HM here. I make videos about topics that are important for whether the future of humanity will be better or worse. Today's video answers two important questions. First question, will the coming transition to battery electric vehicles be slowed down or even stopped because of a lack of copper to make such vehicles? Second question, will the need for more copper create new supply chain risk for the global auto industry? In answering these questions, I'll also consider new technologies developed by Tesla and others that will be able to reduce the need for copper by nearly 50% in the forthcoming battery electric vehicles. With that said, let's get to it. Okay, so let's start this presentation here. The first question we need to answer is, how much copper is there in a typical battery electric vehicle? And I found three sources that all agree that there are about 90 kilo of copper in a typical battery electric vehicles that are made today. And you can see in this figure over here that battery electric vehicles, that's about 190 pounds of copper. And then there's a battery electric bus, of course, that's a bigger vehicle, it has 800 pounds of copper, and some other vehicles. And where is this copper located in a car? Well, it's used in the wire harness, and it's also used in the batteries, and it's also used in the electric motors. That's pretty much the three places where we have copper. So the wire harness in an internal combustion engine car, that is about the same as a wire harness in a battery electric vehicle, and it's about 23 kilo of copper. We can also see that from this graph over here because it has the internal combustion engine over here and it says 47 pounds of copper. So that's about 23 kilo of copper for that wire harness. And the other thing is that a battery electric vehicle, of course, needs a battery pack, and I found a source saying that 8% of the battery pack will be copper. And the battery pack, for instance, in a typical battery electric vehicles like Tesla's Model Y is 530 kilo. So that battery pack will contain 42 kilo of copper. So that's another source of copper in a vehicle. And we have a little picture down here of a battery cell from Tesla. It shows the copper tabs that are sticking out of this battery that Tesla use. This is a 4680 battery that Tesla is now producing in their Texas factory, and also they have a pilot facility in Fremont, California that also produces these batteries. And they use copper to get electricity out of these batteries, and that's shown down here in this picture. And we also have this little picture of the wire harness of a Tesla. Yeah, that looks like a Model S, but that's a wire harness. It's everywhere, of course. And the final place we need copper is motors. And here we know there will be 25 kilo needed for that because 90 kilo is what the total vehicle will have in a battery electric vehicle, and then we subtract the wire harness and the battery pack, then we get 25 kilo. And a normal electric vehicle will have just one motor, and it will be a permanent magnet motor. So what is that? There are two major types of electric motors. One is an induction motor that was invented by Nikola Tesla. It has a stator, that's the outer ring here, that runs some copper wires around a piece of metal that is then magnetized when you put current through it. And it also has a rotor, it's the inner thing here that rotates, and it also has these copper wires around some iron that is then magnetized. And then by controlling the magnetic fields, by controlling how current is flowing through here, then you can make the rotor turn around and drive the electric vehicle here. And the other basic kind of electric motor is over on this left side here. It shows a permanent magnet motor where it's completely the same actually, but in the rotor the magnets have been replaced by permanent magnets that are not induced electrically. They are just permanent magnets, and it has an advantage that you don't use copper, of course. So when we can see the residual is 25 kilo of copper for this permanent magnet motor, and then we look at the induction motor that also needs copper in the rotor. And because that rotor is smaller, the ring of that is smaller than the outer stator ring here, then I'd say, okay, it's probably 15 kilo if the stator here uses 25 kilo. So this induction motor will use 40 kilo of copper, whereas this permanent magnet is 25 kilo of copper. And if you have a vehicle with dual drive and They both have permanent magnet engines. Well, that would be 50 kilo of copper. But actually, Tesla's vehicles, they use a combination of an induction motor and a permanent magnet motor. So they will use just for those motors 65 kilo. So why does Tesla use a combination of induction and permanent magnet motors? It's because Tesla can increase the efficiency of their vehicles by making this combination, because it's known that induction motors have high efficiency at high revolutions, at high torque for the electric vehicles, but at low speed the permanent magnet motor is more efficient. So by combining them and by mostly pulling the vehicle using the induction motor when the car is moving fast and need a lot of power, and also by mostly pulling the car by the permanent magnet motor when the car doesn't need a lot of power, then they can increase the total efficiency of the vehicle and thereby get the range up. I want to say that in a Tesla vehicle that will have both a permanent magnet and an induction motor, the total use of copper would be 130 kilo because of this engine system, and then also add this wire harness and battery electric vehicles. But as we will see, there are ways to cut this copper consumption quite a lot. Okay, so why do we need to worry about copper use in battery electric vehicles? 3 reasons, and the first one is, of course, it costs money. Copper is expensive. 91 kilo of copper, that would be $820 in current prices. And I made a table over here. It took me time to gather all the information in this table, but it basically lists all the kinds of raw materials that we need to make up a vehicle. Graphite, nickel, lithium, copper, manganese, cobalt, rare earth, aluminium, crude steel, and other textile and plastics. And then I took the weight of all that. It sums up to 1.7 tons for an average vehicle. And then I found all the prices that this material cost per kilo in the commodity markets. And then I summed that up, multiplied it, of course, with how much material that's used, and then I summed it up. It's $6,600 for raw materials in a typical battery electric vehicle. And you can see copper is $821. So quite a lot of raw material cost goes into copper. So that's why it's important to talk about. And the other thing is, of course, supply chain risk that may arise in a world where we need to make 100 million battery electric vehicles per year. I have made another table down here where I have multiplied the material we need for one vehicle with 100 million to see how much material we need to make 100 million vehicles. And here you can see for copper, then we need 9.1 million tons of copper. And that compares to 42% of global new copper production. That is 21 million tons. I may add that there is also a lot of recycled copper. So we actually make 9 million tons in addition to those 21 million tons simply from recycling copper from scrap metal. So it is not as bad as it looks that, okay, we need 43% increase in production. But then again, we need more copper for an economy that's based on electric vehicles completely, because we need a charging infrastructure where these chargers will also use copper, and we need a stronger grid with more electricity, of course. So we also need more copper for that. So anyway, I have made this calculation, and I think it's quite interesting that 43% increase in global copper production is needed. If we don't expand current production, then what we will see is that prices for copper will go up. So we have to expand, and we do actually expand, but I'll come back to that later in my presentation. And also a third reason is that copper is a large part of vehicle weight. It's actually 5.4% of total weight. So if we can reduce the copper use, you will reduce the weight of the vehicle, and we can reduce the weight of the vehicle not just by how much we can reduce the copper, because whenever you remove 1 kilo of material from a car, then there's a multiplier effect from that that's larger than 1, because you don't need as much material for structural integrity. And also, if you save weight, the efficiency of a battery electric vehicle will go up. It can actually drive longer for the same battery pack because there's less resistance in the wheels and so forth. So that means if you reduce the weight, you also don't need as much battery pack to do the same range. And that means the battery pack can be reduced in size, and then the weight goes further down. All in all, it means that there's a multiplier effect, that if you say you could remove 1 kilo of weight from the car, you probably have, I don't know, 1.3 kilo of total weight reductions when you incorporate it through structural integrity and also reduce the needed battery pack in size. Something like that. So that's important. Okay, so let's dive a little bit deeper into the supply chain risk and the copper price. Fortunately, the supply chain risk of copper is low because production here is spread on many countries, and China and Russia only supply 12% of the combined world production of copper. And I think China and Russia is our biggest worries currently because Russia has attacked a free and democratic country, Ukraine, and tries to conquer it. And China is threatening to conquer Taiwan also by force. They are definitely showing off a lot of military equipment and making very aggressive moves around Taiwan. So we cannot be sure that relations, well, certainly relations with Russia has been completely ruined, and maybe they'll be ruined also with China if they make a military move on Taiwan. So that's what kind of motivated me to make this video. I want to see if copper is an issue, but luckily copper is not an issue because China only makes 8% of the world's copper. That's almost certainly less than what China needs for their own economy. And also Russia, they only make 4%. So it doesn't really matter. We can do quite well without their copper. Copper production is spread over a lot of countries. Although Chile and Peru together, they command 37% of global copper production. But they're friendly countries. We can rely on supplies from them. And what else can I say? Well, copper can be recycled, and that's a great thing about copper and for supply chain risk. We actually make almost 9 million tons of copper from scrap, simply from recycling scrap. And I think United States, because it has been an industrialized country for so long, they have a lot of scrap and they must have a very high production of copper from scrap. Same with Europe. So I think we are pretty well supplied and it's not a huge concern. Also, a funny fact about copper is that it is considered an early predictor of economic growth cycles. So whenever the economy is strong, we normally see high copper prices, and normally the copper price starts to increase before the data becomes available that the economy is actually doing quite well. So, but the price of copper is of course an instant reaction to what is happening currently in the economy in terms of factory orders for copper and use of copper. So it's a good indicator for economic activity, and perhaps what we see currently with copper price, we have down here, we have the price of copper over a long time period from 1990 and all the way up to 2023. We can see the price of copper is quite high historically, and that does indicate that the economy is not down specifically, although we do talk about that we are in a recession. But I don't think we are. I just think we are in a low growth period, and perhaps the high copper price, I would say that there's a pressure upwards towards higher copper prices because we do need more copper for the coming years to sustain all the extra copper needed for battery electric production, but also for charging infrastructure and all the many new wind turbines and solar power installations that we need. All that needs extra copper, and I think that will create an upward pressure in the price of copper, but not catastrophically. If we have $4 per pound today for copper, that's what we have. Perhaps on the high scale will be $6 for copper in the coming years because the miners need to make a little extra money to expand their production. And down here we have a table that shows the global copper production. Actually, we can see that it has expanded quite a lot, and only in a fairly short time period. For instance, take a look at this one. In 2011, that's this column here, we made about 16 million tons of copper. And then in 2022, it has increased to 21 million tons of copper. And we can also see that there's a projected increase in copper that's quite strong in the coming years, all the way up to 2026. We can make these projections of extra copper production with fairly high accuracy because copper mines are planned many years ahead. There's environmental concerns and planning that, and also there are multi-billion-dollar projects. I think I read somewhere that a new big copper mine was being made and it would cost $10 billion of investments to set that up. So copper mines are huge projects and they're planned many years ahead, and we know when they will start producing and how much they'll produce. So That's why we can do these projections with fairly high degree of certainty. But anyway, the big conclusion here is that supply chain risk is not high for copper, and we're not going to see a 10 times doubling in the price of copper. It will be, I think, maybe $1, maybe $2. In the worst case, that will be 50% increase in copper price. That's what I would estimate. Okay, so now let's start to talk a little bit about how copper can be reduced when we make battery electric vehicles. And let's start by the wire harness. So Tesla, at their Investor Day 2023, they announced that they would replace the 12-volt system with a 48-volt system that also integrates data communication on the same wire harness. That's a big deal because, as you can see here in this slide that they showed at the presentation, there's a long history for what kind of voltage we have used for low voltage systems. And it started out when the first cars were made in 1900 with a 6-volt system and 5 ampere usage on average on these cars. That compares to 30 watt, because just multiply ampere and volt to get the watt usage, total energy usage. As time progressed, more and more electric things came into the cars. And then here in 1960, the watt usage had more than 10 times doubled to 420 watt. And that's also when they decided to change to 12 volt instead of 6 volt. But you still can see here in this graph that measures ampere up here and the years along this axis here, that it's 35 ampere times 12 volt. So that gives you 420 watt. But as the years went by, the consumption of power continued to increase here. So in year 2022, where we still have 12 volt, we use now 2,880 watt. That's a lot. It's actually more than most households use when everybody are home, apart from when they're cooking in their kitchen, then it goes up further. And it continues to increase here in year 2023. Tesla expects to switch to 48 volt. And that would be consuming, from what I can read here on the graph, about 65 ampere or 3,120 watt. But the shift to 48 volt is inevitable because it can actually reduce the use of copper in that wire harness by 75% because you quadruple the voltage here. So that would mean, since we saw that we used 23 kilo of copper in a BEV or an ICE vehicle, that means we could reduce that to 5.8 kilo of copper. I think if it's really true that, as this graph here indicates, that it should happen for Tesla in 2023, I think it will be launched in the first Tesla vehicle in the Cybertruck that is expected to launch this year in 2023. And I speculate that Cybertruck will be running this 48 volt system on 85% of the units that have Tesla controllers, because this is what this graph down here says, that Tesla's in-house controllers, they started out with Model S, they had 20% of the controllers that control power supply and also communication and functioning of any electric device that is in a car. Any electric device that is in a car, be it light or brakes or servo steering or air conditioning, they all need a controller, which is a microchip that controls the power and also the functioning of the device that's connected to that controller. But anyway, Tesla started with 20% of these controllers designed in-house in their second car, the Model S, and then they have increased it to 40% with Model X, and with the Model 3 they had it bumped up to 56% and then 61% with Model Y, and then this Cybertruck is supposed to have 85% of controllers built in-house. And then the next generation vehicle that Tesla also talked about, a lot of technologies that will go into that, 100% of all the controllers will be built by Tesla itself in-house. And that's also why I think that the first vehicle that will be truly 48 volt, that will be this next generation thing. I could imagine that there will still be devices in that Cybertruck that still use 12 volt for their functioning, but in that case, either there is a separate 12 volt system for those devices, or Tesla has simply built some adapters that convert 48 volt from Tesla's wire harness into 12 volt and also converts the communication line. And the third option is that Tesla suppliers can actually deliver electric units that are 48 volt already. So that's what I expect will happen with Cybertruck. And then again, this Tesla's next generation vehicle, it will be 100% built in-house with regard to the controllers, and that's also why I think everything will be 48 volt power at that time. Okay, but we can reduce copper need further by replacing some of the copper wires with aluminum wires instead. But it's not all wires that can be replaced with aluminum, because aluminum has two disadvantages. They are less flexible than copper. Copper bends more easily than aluminum, and also copper has less resistance than aluminum. That means that less heat is developed by these copper wires when current is flowing through, and in some places that might be a problem, that heat. So you cannot use aluminum, that would just create more heat. The reason I expect aluminum to replace some copper wires is that when you go from 12 volt to 48 volt, that also enables that you make these aluminum wires more flexible, because the wires are thinner, and when they are thinner, the wires, they get more flexible, both the copper wires but also the aluminum wires, and therefore it should be easier to replace copper wires with aluminum. And the other reason is that Tesla's next generation assembling system, also presented at this Investor Day 2023, will allow for much better access to install wire harness, and thus further decreasing the need for flexible copper wires. And the best way to understand this and see how this can be true is to actually watch a video from Tesla's Investor Day. I cannot explain it better than they do, so let's just see how they explain it. But first I have to mute my microphone and then I'll play.
A traditional way of making a vehicle is this. You stamp it, you build a body in white, you paint it, and you do final assembly. And what's interesting is these shops are dictated by the organizational structures that exist. And they're dictated by the boundaries that exist in the factories that are laid out. If something goes wrong in final assembly, you block the whole line, and you end up with buffering in between. This is at the tail end of its manufacturing optimization. Henry Ford first invented this assembly line in 1922. It's been 100 years, and it's really hard to make a change after 100 years. And when you watch it happen, it's actually really silly to a guy like me. You take all these stamp panels, you put them together, then you put them in a framing station, you build a body that looks something like a car, you put the doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings that already exist. I wish it went in like this big piece like this, but there's actually people coming in and out of the car. There's awkward movements. Then we lift the car up, we put stuff from underneath it, we put it down, then we put the seats in the car, and finally we close it all out with glass, and we bring those doors that went away for a trip, and we put them back in the car.
So what you should have noticed here in this video is that the current way of building a car is that you build the entire body of the car, and that naked body is then you start to put a lot of things into that body in order to assemble the entire car, and the car moves down an assembly line and gets more and more stuff put into it. But the fact that you have this body means that to get wire harnesses into that car is hampered by the limited access you have because of this body structure that's already built. And what Tesla is proposing in their next generation vehicle is that they don't build an entire body and then start putting stuff on it. Instead, they will build the car in separate parts, as we can see down here in this illustration. They build the left side in one shop and right side in another shop. They built the floor in another shop. Then they built a front of the car in one shop, a rear in the car in another shop, and other stuff in other parts of the factory. And when they build all these different things, then they start to assemble the whole car as one whole. And that just means that you could put the wire harness in for all of these sub-components of the car. And then when you assemble the car, you can just bring together the communication and the power lines by pulling in. I could imagine something that looks like a horseshoe that you just put on top of it. It could be a stiff thing. It could probably even be mounted by a robot, not a human, and then the whole car has communication and power. But let's look at this video that Tesla has also made of this, because they explain it much better than I do, I think.
In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently, we only paint what we need to, and then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it, and it means we're doing more work on the car more of the time. And then, when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
So that's how Tesla plan to make their next generation vehicles in Mexico. And I think it looks pretty smart, and I really hope they succeed in making this work as they intend, because it will be a revolution in itself in the auto industry if this will be the new way to assemble cars in the future. And so what can we sum up here? The 48-volt system could cut copper in the wire harness from 23 kilo to about 6 kilo. And in my opinion, this new assembly system could further help to cut copper use to 3 kilo simply by replacing some copper wires with aluminium. And aluminium it's cheaper than copper, and yeah, it's also lighter, less weight. So you also have weight savings. That's a benefit of aluminium. But I think that's enough for this slide. So what else can Tesla do to reduce the copper? They of course have the motors, and Tesla's current all-wheel drive Model 3 and Model Y, they likely use those 65 kilo of copper in their two electric motors, of which 25 kilo is in the permanent magnet motor and 40 kilo is for the induction motor that likely needs 15 kilo more copper for its rotor that uses copper, as I showed you in this illustration from before, with an induction motor that uses copper windings both in the rotor and the stator, whereas permanent magnet only uses copper winding in the stator but not in the rotor that just uses permanent magnets. However, Tesla could reduce copper simply by replacing this induction motor that they use in their vehicles today with this permanent magnet motor that uses less copper. And one of the really big things that Tesla announced at Investor Day 2023 was that they developed a new and more efficient permanent magnet motor that only cost $1,000 to build and doesn't use any rare earth elements. This is a big deal because the cost seems to have come down by about 50% for this motor compared to what it is today. And this no rare earth elements in the motor, that eliminates a huge supply chain risk that Tesla have with making their permanent magnet motors today. And I made actually a video specifically about that. That's my video number 17, and you can find it on my channel and watch that if that interests you. In my opinion, I think it's obvious that Tesla will use this new permanent magnet motor to replace their induction motors because, as I said, it only costs $1,000 and it no longer uses these rare earth elements. There's only one argument for keeping the induction motor, and that is when you drive the car very fast or you hit the pedal and do a quick acceleration, then the induction motor is more efficient than a permanent magnet motor. But I think it's marginal what you save in electricity in these instances because you don't do that very often. And I think it's not enough to save the induction motor from Tesla's future lineup of vehicles. I think they will all be permanent magnet motors. So that's about it for this slide. Now there's one more thing that Tesla can do to reduce their copper use in their motors, and that is to use a higher voltage, of course, in the motors, just like we saw it with the low voltage system. They could raise that from 12 volt to 48 volt, but they could also raise currently Tesla motors use 400 volt, and they could raise that to 900 volt. I'm not sure about 900 volt. That's something I just guess. It could be anything really from 800 volt like Porsche has done in their Taycan, and also there are like 6 cars that are developed by other automakers that are BEVs and that have used 800 volt systems. So maybe Tesla will also use that, or they will use their own standard. Tesla normally go their own way, so they probably use another thing than 800 volt. I think they'll use 900 volt, and if they do that, then they can reduce copper in its motors by 56% as calculated here. And the other advantage of going to a higher voltage is that charging power could also reduce charging time, because charging power could be higher by having a higher voltage and enable fast charging for large vehicles. The Cybertruck is coming. That's a larger vehicle. It will have a larger battery, perhaps 40 or 50 kilowatt hours, and it would be a benefit for that one to have a higher voltage system, so they can charge at a higher rate, so it doesn't take so long to charge this vehicle. And I'm pretty sure Tesla will do it. Why didn't they talk about it at Investor Day? I think they don't want the Osborne effect, because if people know that Tesla is now going to make this shift with new powertrains and higher voltage, then some people will simply hold on and wait until they can get a Tesla with a higher voltage. Also because it's a big change, and Tesla also needs to change their charging stations. The current charging stations that Tesla has built are all based on this 400 volt system, and they need new chargers to be able to do 900 volt. I don't know if Cybertruck really is 900 volt, then they'll probably have a built-in adapter in the Cybertruck so it can also charge at existing chargers. But Tesla will also have to build new chargers that has 900 volt charging for sure. And maybe this fourth generation charging station that Tesla has just started to roll out, but they haven't told much about what the specifications of that is. I wouldn't be surprised if it's actually capable of charging at 900 volt. I believe they have a 1000 volt rated AC to DC converter in them, so it should be possible. But let's see what will happen when we get more information about that. And also, I should mention that what about batteries? That's the last big place where you use copper. I don't see any technologies that can change how much copper we can use in batteries. Maybe that's just my own ignorance. Maybe I don't know about something that's coming up. But copper is used in batteries, and they're used because it's a very efficient current collector, and it's also an efficient distributor of heat inside the battery cell, so you can cool the battery pack more easy if it has copper in them, and it does. So it's not easy to replace. So what does all this sum up to? I have in this table down here, I have calculated for a rear-wheel drive vehicle with one motor, we use 23 kilo of copper for the wire harness, and we use 25 kilo here for the permanent magnet motor, and then 42 kilo for the battery. That adds up to 90 kilo. And for the next generation model 3 and Y like vehicles, and the one that'll be built there in Mexico, well, I expect only 3 kilo of copper needed for the wire harness, and 11 kilo for the motor, and 42 kilo still for the batteries, and that sums up to 56 kilo, so almost a 40% reduction in copper use. And if we consider an all-wheel drive vehicle with two motors, again, we have a reduction in the wire harness from 23 kilo to 3 kilo of copper, and in the rear motor we have a reduction from 25 kilo to 11, and in the front motor we will have a reduction from 40 kilo to 11 kilo, because we go from 400 volt induction motor to a 900 volt permanent magnet motor with no rare earth elements in it. That would be 11 kilo of copper. Anyway, it sums up to 67 kilo of copper, down from 130, so that's almost a 50% reduction of copper usage for these vehicles. So what's the big conclusion for this presentation? Well, it is, in my opinion, that copper is not a potential showstopper for battery electric transition. We saw this table here that I made that we actually produce quite a lot of copper currently, 21 million from mining, plus another 9 million tons per year from scrapped copper. That would be 30 million tons. And if we assume we have this 90 kilo or 91 kilo per vehicle used, and we start to make 100 million of these vehicles, well, that will only represent 43% of the current copper production for mining. But we also have this scrap copper, and we can make reductions in the amount of copper we need for these vehicles. Also, it's not done with copper reductions here. Instead of using so much steel, we can see here in this table also that we use 1 ton of steel, and then we use less than 200 kilo of aluminium. We could could use more aluminium and less steel to make the vehicles significantly lighter. That will increase cost because aluminium costs more than steel, and it's also more costly to manufacture stuff in aluminium than in steel. But we could reduce the weight and thereby increase the efficiency of the vehicles, and thereby the battery needed will be smaller. So I think all in all, we have enough copper in this world, and we can expand our mine production to cover what we need in order to get to 100 million battery electric vehicles per year in the auto industry. And also, copper supply chain is not something to worry about because it's spread over many countries, and the two critical countries, Russia and China, do not control a large part of this copper production. I think it was down to 12% from these two countries, and that's probably less copper than they use themselves, so they have to import from other countries just to cover their own needs, especially China, probably not Russia, they export. So that would be my presentation. I have some sources and attribution for the previous slides. Everything I've said and postulated here, I have links to it, and you can download my presentation down below by following the links, and then you can click these sources. My forthcoming videos will do the same analysis that I've just done for copper, but now with regard to lithium and graphite that are also needed for making battery electric vehicles. So if you think that sounds interesting, consider subscribing to my channel so these videos will show up in your YouTube feed. Thank you for watching my video. I wish you a healthy and fulfilling life in freedom and democracy.